This is a multimedia presentation that is a supplement to the Sustainable Country Living book. The topic is geothermal, which dovetails with Chapter 10 in the book, Alternative Energy Geothermal. Our topic is geothermal energy, which is utilizing the heat underground to help cool and heat a home or generate electricity commercially. Renewable energy geothermal.
The Earth's crust is made of rocks and water. Deep below that is a layer of hot, molten rock called magma, which is even hotter than the sun's surface. The heat just over 6 miles below the surface contains 50,000 times more energy than all the oil and natural gas resources in the world. Releasing a small amount of that heat in the right way can create electricity. A well drilled a couple of miles deep can capture the rising hot water and steam. That steam spins a turbine, and a generator produces electricity.
Renewable energy geothermal. So we have magma, which is a hot layer in the earth. If you go 6 miles deep, it holds 50,000 times more energy than all the oil and natural gas in the world. Wells, a couple of miles deep, can create electricity. So how do we use geothermal?
How do we capture Earth's incredible energy? There are a few ways. We can tap into the consistent temperature located just a few feet into the ground to use the Earth like a thermos, heating buildings in the winter and cooling them in the summer. Or dig deeper to access the Earth's heat. In some places in the western United States and Hawaii, this heat is shallow, less than 3 kilometers deep. But this heat is everywhere. No matter where you are on Earth, you may have to drill down a little deeper. These geothermal resources provide energy that can be used on both large and small scales. A geothermal power plant uses heat to produce steam, which turns a turbine, which drives generators and converts the power into electricity. Or the heat can be applied directly for various uses in buildings, roads, agriculture, industrial plants, and even homes. In 2019, United States geothermal power plants produced 16 billion kilowatt hours of electricity, all in the western United States. That's only a small fraction, less than 0.5% of the total U.S. utility-scale electricity generation. And there is so much potential. In fact, there is more than enough heat below the U.S. to provide all its needed energy. So why don't we use more? Geothermal is one of the least explored sources of clean energy. With such a long track record, scientists continue to work on better ways to capture and use this clean, natural, renewable resource to be able to use it anywhere in the U.S.
How geothermal energy works. Large geothermal energy plants used to be limited to active areas, but new technology allows for more productive options. Dry steam geothermal is one method of creating electricity from the heat of the earth. Another one is called flash steam geothermal. The Northern California coast produces 60% of California's electrical generation using geothermal.
Iceland has moved from being a poor country primarily using imported oil and coal. Since then, we have transformed our energy system.
And geothermal energy and renewables became for Iceland what chocolate and banking are for Switzerland.
Since it creates heating for around 9 out of 10 houses and almost 30% of all our electricity.
And if you're really clever, you can direct that into a turbine and generate electricity.
And then, after using it,
the cold water is pumped back into the earth, and inside the earth, it's heated again on the way to the producing valve again. So it's like a cycle of hot and cold water.
An almost limitless renewable source that can be used for heating and electricity. And geothermal energy could be a smart choice.
It is available 24 hours per day, 365 days per year, in contrast to solar on cloudy days or wind when the wind doesn't blow.
Geothermal is renewable. Iceland was energy poor. Now, 9 out of 10 houses are heated by geothermal. It is almost a limitless renewable source, available 24/7, 365. Geothermal heat pumps.
We all want to save money heating and cooling our house or office, right? The answer may be under your feet, literally. Much of the heating and cooling can come from the ground, below the surface, with something called a geothermal heat pump. You see, below the frost line, about 10 feet down, the Earth maintains a nearly constant temperature of 54 degrees. We can tap into this energy to provide heating in the winter and cooling in the summer. Okay, now here's how it works. Bury a loop of pipes, called a heat exchanger, just below the surface, and fill them with water or a water and antifreeze solution. During the winter months, the air is usually cooler than the temperature below ground. The solution circulates in a loop underground and absorbs the Earth's heat. This heat is brought to the surface and transferred to a heat pump. The heat pump warms the air, and then your regular heating system warms the air some more to a comfortable temperature. Finally, ducts circulate the air to the various rooms. Now, a huge benefit is that the geothermal system doesn't have to work as hard to make people inside comfortably warm, and you save lots of money on your heating bill. In the summertime, the system works in reverse. When it's hot outside, the temperature below the surface is cooler than the summer heat. So the fluid in the loop absorbs heat in the building and sends it underground. The ground's lower temperature cools it, and it's circulated again and again. Now you're saving money on air conditioning. Now, this church uses a large geothermal heat pump to heat and cool the building. It has a very big parking lot, which lets it spread out its loop horizontally. But if you don't have all that space, you can go straight down and use a vertical loop system instead. Geothermal heat pumps can be used just about anywhere in the U.S. because all areas have nearly constant shallow ground temperatures, although systems in different locations will have varying degrees of efficiency and cost savings. The constant temperature of the Earth just below our feet is a sustainable resource, literally in our own backyard. It's a clean energy source ready for us to use to heat and cool our homes and buildings while lowering our utility bills.
Geothermal heat pumps. Saving money on heating and cooling costs can be done by using geothermal heat pumps. A geothermal heat pump, known as a GHP, is a heat exchange process that takes the heat from underground and uses it to a geothermal heat pump, GHP, allows the constant temperature underground to be used to help regulate the heat and cooling in a house. 10 feet down, it's a consistent 54 degrees, and buried heat exchanger piping in that level can then be used in the house. Heat pumps then help heat and cool the house. This is a sustainable resource. New geothermal technologies.
Unlike solar and wind, geothermal energy could provide a more stable supply of clean power while taking up barely any land. On the other hand, current drilling techniques can't affordably reach the hottest spots of the Earth to unlock that potential. In fact, penetrating deep into the hard rock is tricky and expensive. Along with exploration, digging wells accounts for about 40% of the total upfront cost of a geothermal plant. And of all the options, binary cycle power plants are the newest and most sustainable ones. Unlike other designs, binary plants don't use the underground hot water to generate steam directly. To be more specific, after extracting it and further heating it up to about 400 degrees Fahrenheit or 204 degrees Celsius, they run it through a heat exchanger. Here, the geothermal water transfers its heat to a secondary liquid with a much lower boiling point. This then generates the steam that will spin the turbine. The plant includes a condenser to convert the steam back into a liquid and reuse it. Leveraging this closed-loop binary system, the water won't boil off the geothermal fluids, which, other than water vapor, contain carbon dioxide, hydrogen sulfide, and other toxic compounds. You can probably see why this is a greener and preferred alternative to dry and flash steam plants. The overall geothermal potential is huge. According to Ultra-Rock Energy, harvesting only 0.1% of the planet's heat could satisfy the world's energy hunger for 2 million years. Now, given how cool that is, or hot, why did geothermal energy account for only 0.55% of our global electricity generation as of 2018? Mainly because the accessible part of that is heat scattered across the Earth's crust. In fact, most hydrothermal reservoirs, such as volcanoes, springs, and geysers, are only found along tectonic plates. In addition, the water filling shallow geothermal pockets isn't hot enough to make energy harvesting cost-effective. Not to mention the technical and economic hurdles of reaching hotter spots using current drilling techniques. Yet, thanks to fusion-inspired drilling technology, the true potential of geothermal power could be closer than ever. This innovation could get us below 10 kilometers or about 6 miles in a much more cost-effective fashion. Down there, geothermal sources have much higher temperatures and are more widespread. While being cost-effective, the potential of solar and wind farms is undermined by their intermittency. Instead, a 24/7 green energy source like geothermal could give us an extra powerful weapon against global warming. And speaking of weapons, let's dig in deeper into how death rays, again, not a death ray, could push geothermal energy to a new level. It all began with the work of Paul Waskoff, a senior research engineer at MIT's Plasma Science and Fusion Center. In 2012, he demonstrated the application of a gyrotron to vaporize rock instead of grinding it. This high-powered vacuum tube generates a beam of millimeter-long radio frequency waves, which have been used to heat up plasma and control its temperature in fusion reactors for the last 50 years. Hijacking this fusion tech, Waskoff envisioned drilling ultra-deep geothermal boreholes. So how does it actually work? You would have a metallic tube embedding the gyrotron, blasting high-frequency electromagnetic waves to fuse the underground rock. The system injects a gas for cleaning up the post-vaporization mess. To be more specific, the gas cools down the hot vapors, which condense into nanoparticles. These are then flushed out of the well by the high-pressure stream, but you wouldn't use this sophisticated drilling for the entire process. According to the US Department of Energy's GeoVision report, leveraging these untapped subterranean heat sources could increase geothermal-based electricity 26-fold by 2050. In addition to a wider availability, when you go below 10 kilometers or about the 6-mile mark, you'll find the so-called super hot rock, or SHR. Those geothermal resources have temperatures about 375 degrees Celsius or 707 degrees Fahrenheit. Now, under these conditions, a geothermal plant can tap into supercritical water, which is more energy dense than non-supercritical counterparts. A well plunged into an SHR could yield up to 10 times more energy than a conventional enhanced geothermal system. Now, based on the technological and economic feasibility studies conducted by Ultra-Rock Energy on the Newberry volcano site, SHR would reduce geothermal's levelized cost of electricity, or LCOE, by 50%. On top of that, the company estimated that SHR-based geothermal could have a lower LCOE than onshore wind and even solar. Now, the development of fusion-inspired drilling would let us tap into plenty of superhot fluids by overcoming geographical and geological limitations. It could also unleash a perpetual spring of geothermal power for a zero-carbon energy-independent world.
New geothermal technologies. Binary cycle power plants are the newest and most sustainable method. It's a heat exchanger approach. It's greener and a preferred method. Death ray drilling method uses gyrotron to reach super hot rocks, SHR, at 6 miles deep. Types of geothermal heating systems.
When building a house, homeowners have several ways to power their heating and cooling systems, like oil, natural gas, or electricity. But there's another option that's right below our feet. You can install geothermal heating and cooling at your home. But is it worth the cost, and how does it hold up? I'm Matt Farrell. Welcome to Undecided. Heating and cooling systems are an essential part of our homes, but it comes at a cost. According to the 2021 Annual Energy Outlook from the EIA, space heating represents 15% of total household electricity here in the US, while space cooling accounts for 16%, so together, they share about 31% of the total electricity use in the country. But that's going to vary based on the region. Along with electricity, the main heating fuels are natural gas and oil. Now, while oil usage is low across the US, it's still, sadly, widely used here in the Northeast where I live. And we're talking about 81% of all heating oil is used in this region. But thankfully, one alternative that's slowly getting steam is using geothermal energy directly from the ground to heat and cool your home. If you're interested in how geothermal energy is used to produce electricity, I have a video on that topic too. Geothermal systems have been in place since the 1940s, initially providing water heating. But with the technology's evolution, these systems have been used for different purposes such as electricity generation and heating and cooling systems, also known as ground source heat pumps, or GSHP, which take advantage of the ground's stable temperature to provide heating and cooling. Basically, a geothermal heating system is made up of fluid-filled tube loops to exchange heat with the soil, and a heat pump that removes the heat from that fluid, concentrates it, and then transfers it to the building using ductwork. That part looks pretty familiar to any other forced air heating system that you've probably seen. The heart of a geothermal heat pump is made up of a heat exchanger, a compressor, and a control system that regulates the process. The fluid that's used can range from groundwater to a water mixed with antifreeze or another suitable refrigerant that circulates throughout the ground loops. But to understand that heating and cooling process, it's important to know that heat always flows from a higher temperature fluid or body to a lower temperature one. For example, when you put an ice cube into a glass of water, it melts, right? That's because the water has a higher temperature and more heat than the ice cube. So the heat is transferring into the cube, which causes the ice to heat up and melt. So taking that back to the heat pump, during the winter, the temperature underground is higher than the surface air. So the cool liquid traveling from the house down inside the loops absorbs heat from underground, bringing it back up into the house. And the heat pump compresses the liquid, increasing the liquid's temperature, which warms the air. And the warmed air is circulated around the house and exchanged with the cooler air. The cooled liquid from this process is pumped back into the ground to continue the cycle, forming a closed loop. In the summertime, this process is reversed. The lower temperature refrigerant absorbs heat from the house, which now has a higher temperature than the underground, so it's the exact same principle. The heated liquid transfers heat from the house into the ground and returns back up into the house, cooled off. They can be subcategorized into 4 types according to the orientation of the heat exchanger loops in the ground. In vertical loops, as the name implies, they're vertically oriented, and they require several holes to be drilled straight into the ground. The number of holes, their depth, the spacing between them, and the volume of fluid that's in the tubes depends on the soil, temperature variations, and the house's heating and cooling needs. A great advantage of vertical systems is that they can be installed within a very small area. Horizontal loops, just as the name implies here too, are composed of pipes that are placed horizontally in the soil, with the tubing being buried about 1 to 3 meters underground, but the length can be up to 120 meters. They take up a lot of room. If the loops are installed too shallow, they can run too cool in winter months. Horizontal loop systems are usually installed in locations with larger amounts of ground available for digging, such as farms, country houses. Like I said, you need a lot of space. There are also slinky coil loops, but not that kind of slinky. These are very similar to the horizontal arrangements, but they coil the tubing to overlap itself to save space. So these loops provide the same distance of piping with less area. However, these systems require more coiling per kilowatt of capacity. And finally, pond loops, which are submerged systems that are installed in bodies of water near the house. These systems don't require drilling or digging, which can reduce costs, but the water needs to be deep enough so that the loops aren't subjected to surface temperatures. Geothermal systems have some advantages that have raised interest for homeowners around the world. These systems can provide significant savings for heating and cooling. They can work well in almost all climates, they're environmentally friendly, last longer than conventional heating and cooling systems, sometimes dramatically longer, and require low maintenance.
Types of geothermal heating systems. Conventional heating options are oil, natural gas or propane, and electricity. Ground source heat pumps come in 4 different varieties. The first is a vertical loop configuration where the piping goes straight down. And then the next option is horizontal loop. This is more common because you only have to go 10 feet deep and the piping goes horizontally in the trench. The next one is the slinky coil loop configuration, which can either be vertical or horizontal, but instead of just a straight line of piping, it makes loops so that it doesn't take as much ground space. And the last option is a pond loop configuration, where the coils are actually in water nearby the house. The advantages of geothermal heating systems is they're environmentally friendly, and not only can it heat, but it also provides cooling, unlike other methods of heating houses. Disadvantages are it's expensive to install, and it is running on electricity. Why Matt Farrell chose geothermal heat.
I'm building a new super energy efficient home with the goal of being net zero energy, meaning that my home will generate as much energy as it uses over the course of a year. And to hit that goal, the first step is to build something that's going to be super energy efficient. From my geothermal system, getting the metal roof on, roughing in the electrical and the plumbing, my wife and I have gone a little nuts in what we're putting into the house. I mean, who am I kidding? It's me pushing this, not my wife. But I keep joking with her that I feel like John Hammond building out Jurassic Park.
Spared no expense. We spared no expense. Spared no expense. Spared no expense.
I just hope I don't come to regret that like John Hammond did. Now, one of the big updates I wanted to run through was my geothermal system and why I decided to go that route. it shouldn't be a surprise that I'm all in on heat pumps. I've put out quite a few videos on why we should heat pump all the things, and my house is no different. I'm going to get into a lot more detail in a future video, breaking down the costs and analysis of the system I installed, but the TLDR of why I went with geothermal versus an air source heat pump system, or even a mini split system, came down to efficiency and longevity, not just cost. Getting a geothermal system is typically a lot more expensive than a typical air source heat pump, but there are incentives that bring that cost more in line, but it is still more expensive up front. However, the geothermal system is more efficient and can be tied into my hot water generation, and that combo will save me money and energy long term. This is our forever home, so we're looking to live here for 20 to 30 years, which means we'll be getting our money and quality of life improvements out of the slightly higher upfront cost. It was an interesting experience getting the system designed and seeing it installed. We hired an independent mechanical engineer that had no association with any company to design a system that would meet our goals. We walked through some different options like air source heat pumps, but ultimately we landed on a geothermal system. In any case, the independent designer we hired calculated that we'd probably need about 25,000 BTU per hour for heating on the coldest days, which is around -10 degrees Fahrenheit or -23 degrees Celsius, and 15,000 BTU per hour for cooling in summer on the hottest days, which would be around 90 degrees Fahrenheit or 32 degrees Celsius. Now, ideally, we'd have something around a 2-ton system, but since we ended up going with the Water Furnace Series 7, the smallest available is a 3-ton system. The fact it's a little oversized shouldn't be an issue since it's a variable speed system and can easily run partial load demands. In fact, it might actually help us since it'll be running at lower percentages most of the time, which should make for an even quieter operation. But it's the geothermal well that I was crazy interested to see built out. But there are 2 typical options for a ground loop. The first is a horizontal loop, and the second is a vertical loop. The more affordable horizontal loop is where they dig down ideally 6 to 10 feet over a large area of your yard. Then they put in a single run of tubing in small loops that feeds back to the house and cover it back up. Given the size of my yard and its location, a horizontal loop wasn't the best option for us, so we had to go the more expensive route with a vertical loop. And drilling a vertical well isn't that different from drilling a well for water, but as somebody who's never seen that process in person, I was fascinated by this. Now the drilling truck was backed into my backyard, and then the crew had to dig down about 5 or 6 feet with a backhoe before they could even start. And I live in New England, and the weather wasn't cooperating the day or two before, and we had a cold snap which froze the ground, so they had to dig out some of the frozen dirt by hand with the help of a jackhammer. Once they got past that, they were able to get the drill set up. And they dug a little trench system that they filled with water and added a material which is usually something like a bentonite additive. It creates the drilling mud. Now the mud is essential for drilling because it forms a thin film on the walls of the borehole to seal it and prevent water loss while drilling. It also supports the borehole wall to keep it from caving in. Now during the drilling process, a drill bit is attached to a long pipe and they keep adding onto it as it goes. After the hole is completed, they feed a closed loop polyethylene pipe into the hole and then fill the hole with grout. Now, the grout is extremely important because it helps to transfer the heat from the surrounding rock and dirt into the tubing and ultimately the fluid inside. In my case, they drilled down about 400 feet and only needed to do 1 well to support the heating and cooling demands of my HVAC system. Someone else's home might need more wells or deeper wells. And once you get down to about 6 to 10 feet below the surface, the earth becomes a consistent 50 degrees Fahrenheit or 10 degrees Celsius. That's critical for the efficiency of the heat pump system because no matter what time of year it is, we can always count on having that 50 degrees Fahrenheit to pull heat from in the winter or move heat into during the summer. The exterior air temperature is less of a concern, but by using a compressor, they can boost that heat from 50 degrees Fahrenheit up to comfortable temperatures for your home. If you're curious about the liquid that's going to be pressurized into the tube, it's going to be Environol, which is an alcohol-based antifreeze that makes sure that it won't freeze up in the middle of winter. The well tubing was run towards the house where it connected up to the tubing that had been pre-installed in the foundation and up into the mechanical room. It's in there that you'll find the water furnace system and all the ductwork that feeds the forced air throughout my house. One last note on the geothermal system in the mechanical room is that there'll be a desuperheater that will take excess heat from the geothermal system and hold it as warmed water that feeds into a heat pump water heater from Rheem. Not only is a heat pump water heater one of the more energy efficient ways to create hot water, but it'll be even more efficient with the pre-warmed water coming from the geothermal system.
Why Matt Farrell chose geothermal heat. If this topic interests you and you're considering it seriously, I would recommend looking at Matt's 1-year explanation of the hydro, solar, and geothermal system. In this video, he goes into detail explaining the successes and the lessons he's learned, as well as cost calculations of installation and over time paybacks from incentives and programs available. In this 1-year video, Matt explores in detail what it cost and how he went about installing geothermal, vertical in his case, in his home, and how in combination with his solar and connection to the grid and exchanging with the power grid through net metering, what his projections are in terms of return of investment over the next 20 or 25 years. To be aware of new videos like this one, be sure to subscribe to the Preparing for the Time of Trouble channel. For more free videos and downloadable audio podcasts, as well as handouts, go to www.preparingforthetimeoftrouble.com. Topic categories include recordings of live seminar presentations, country living, sustainable gardening, homestead remedies, how to be self-sufficient when the grid goes down, wild edible and medicinal plants, hydrotherapy, and end-time Bible prophecies. To take advantage of these free resources, go to preparingforthetimeoftrouble.com.